In the previous lecture we began a discussion of the equations for modeling semi-classical transport. So first we mentioned what is the organization of these equations and boundary conditions. So we said that the equations of semi-classical transport can be divided into two sets. One set is the electromagnetic fields, equations for electromagnetic field, and the other set is the transport equations. The equations of electromagnetic field, they yield the values of electric field, the magnetic flux B, and the force on an electron due to electric field and magnetic flux. To yield these quantities, the electromagnetic field equations require a knowledge of the electron concentration, hole concentration, electron current density and hole density. Now these quantities, namely N, P, Jn and Jp, are yielded by the solution of the transport equations, which take as input the electric field, the magnetic flux and the force on an electron as inputs. Okay, so this is how the electromagnetic field equations and the transport equations are coupled to each other. We also mentioned that one should not forget about the boundary conditions, because the non-contact and contact boundaries of the device impose conditions on the electric field, the magnetic flux and heat flux. So these are required for solving these equations. Then we discussed the equations of electromagnetic field in detail. We said there are 5 equations which include 4 Maxwell's equations and 1 Lorentz force equation. Then we mentioned what are the approximations of these electromagnetic field equations, namely the quasi-static approximation, in which we neglect the time varying nature of electric and magnetic fields, and we neglect in fact the effect of the magnetic field itself. Under these approximations, the electromagnetic field equations reduce to 3 equations, namely the Gauss law or the Poisson's equation, then the equation which relates electric field to the gradient of the potential, and the Lorentz force equation which relates the force on an electron to the electric field. Then we began the discussion of the transport equations. We mentioned that because the situation in a semiconductor is very complex, there are a large number of carriers all colliding with each other, and then there is a directed motion superimposed over random motion. There are a variety of approaches to deal with this problem. Therefore we have a large number of equations and different levels of equations. Now since we have a large number of equations, we brought out an important point about these transport equations, namely that most of them can be cast in the form of a conservation, balance or continuity equation. For example, we took up the whole continuity equation which we have done in the first level course, and we pointed out what is its form. It consists of a time derivative of a quantity on the left hand side, the spatial derivative of the flux of the same quantity on the right hand side, and some source and sink terms. And we said we will show that the transport equations that we are going to discuss will mostly be of this form, and therefore it is not at all difficult to become comfortable with a large number of equations. Now with this background we proceed further in this lecture on the transport equations. To start with, let us discuss the micro to macro level descriptions of electron transport. So the microscopic level and the macroscopic or the gross level. So progressively, how do we go from microscopic level, the small scale, to the large scale? We shall show 4 different levels of descriptions. The most fundamental level, we look at the device current in terms of the state of individual carriers, regarding them as waves. So this approach in which we regard the carrier as a wave is valid when the device size or the mean free path between 2 collisions is less than the average de Broglie wavelength of an average thermal carrier. The other 3 levels of transport would be semi-classical, and these will be based on the assumption that the device size or the mean free path between two collisions is much more than the thermal average wavelength of an electron. Let us look at the most fundamental level. Here we find out the current based on the states of individual carrier, okay, regarding the electron as a wave. So we take the group of electrons. For each electron we find out the state of the electron by solving Schrodinger's equation, and from a knowledge of this state we try to derive the current. As against this, the next approximate level is that in which the carrier is regarded as a particle with an effective mass in between any two collisions. So here we find out the state of the carrier using Newton's second law, and based on the knowledge of this state, which consists of actually a knowledge of the position of the carrier and the momentum of the carrier. So for each carrier we find out the position and momentum, and from this description we try to derive the carrier concentration and current density. The next approximate level is an ensemble viewpoint in which we regard the carriers, or we treat the carriers in terms of their groups. So in this ensemble viewpoint, the most fundamental level, we look at the carriers from their distribution over the momentum. So this f here is the distribution function, which is a function of the position, the momentum and the time instant. Okay. Now let us explain this part in little bit detail. What does this shape of the distribution function mean? So in many cases the number of carriers in the device is so large that it becomes a complicated matter to analyze the state of each carrier and from there build up the picture of the current. So instead of that we are looking at the carrier as a group. So now suppose this is our device, and we divide this device into local volumes like this. Now we look at a volume here and we look at the electrons which are present in this volume. Now as we know, all these electrons will not have the same momentum, okay. Their momentum will be distributed randomly. Now what is the shape of the distribution? That is what is given by this distribution function f. So what it says is that there is a certain momentum range in which there will be a maximum number of particles, and then beyond this value on the either side the number of particles having larger momentum will be smaller and smaller, and number of particles having smaller momentum than this value also will be reducing. So that is how you get a distribution like this. For example, in terms of the distribution function, if I want to know the number of carriers, then I can take this local volume. I will find that whatever electrons are there in this, they will all be distributed like this. So if I take the area under this curve and divide this area by the local volume, then I will get the carrier concentration n. Just the area under this curve will tell me the number of carriers in this local volume. Now in terms of this distribution function, how do I know what is the current? So I can find out the momentas of different particles, okay. For example, I know that the number of carriers denoted by this area have momentum around this value. A number of carriers denoted by this area have momentum around this value, okay. So like this, from a knowledge of the momentas of different groups of carriers, I can find out the current. because after all we know that the current or current density is nothing but the momentum in a particular direction of interest. So this is the fundamental ensemble viewpoint where we are treating the carriers in terms of groups and we are analyzing the momentum distribution of these carriers, and from a knowledge of this momentum distribution we are building up the description of the carrier concentration and current density. The most gross level or macroscopic level of description is in terms of carrier concentration n and velocity b. It turns out that the level of detail provided by the distribution function is not required in many situations. All that we need in many situations is a knowledge of how many carriers are present in a local volume and what is the average momentum of these carriers. We need not know the distribution of these carriers over momentum, right? Even if I know what is the average momentum of the whole group, I can work with that for most applications. Now that is the approach, that is the grossest approach and most commonly used. So that is what is described here in terms of this diagram or illustrated here. So for example, this distribution of electrons concentration Nx, this line is obtained from the area under the curve here. So this diagram illustrates the distribution of carriers over momentum at 3 locations, x equal to x1, x equal to x2 and x equal to x3. So you find that the momentum, average momentum is progressively increasing as you move from x1 to x2 to x3 because the peak point in this distribution function is moving to the right. So the average momentum information is in some other form the information about the average velocity of carriers. Therefore you find here that the carrier velocity is increasing as you increase with x. So at x1 the carrier velocity is this much, that is a reflection of the fact that the peak is at some momentum here, and this momentum, whatever velocity you calculate from this momentum is actually what you have put here. At x2 the distribution is like this, so you take this value here, momentum value, from there you find out the velocity that you get here, and similarly for x3. So you find that the velocity is increasing because here the distribution function is moving to the right as you go from x1 to x2 to x3, and on the other hand the area under the distribution is going on decreasing, and since the area divided by the local volume represents the carrier concentration, therefore the carrier concentration is decreasing. So this picture about Nx and Vx is obtained by averaging of the picture that you have here, and this picture in fact is sufficient to give you the current, because you know that the current is given by the product of the electron concentration and the velocity, and of course you multiply by the negative of the charge. Now in some cases, to analyze the transport phenomenon completely, you may also need the knowledge of the average energy. Apart from the average concentration, the average momentum in a local volume, you may also need knowledge of average energy. Even that can be obtained from the distribution function, and this we will see later. Okay. So to summarize, we have given here 4 levels of description of carrier transport from microscopic level to macroscopic level. The most fundamental level is individual carrier viewpoint with carrier as a wave. The next level is individual carrier viewpoint but with carrier as a particle. Then the next level is a viewpoint where you treat carriers in terms of an ensemble or groups, and you look at their distribution over momentum. And the most gross level, you don't bother about the distribution over momentum but only bother about the average quantities such as carrier concentration, momentum and energy in a local volume, and analyze the device in terms of these. Now we will proceed to outline each of this method of determining current in detail. let us look at the transport equations from the individual electron viewpoint. So fundamental level is carriers as waves, the next level is carriers as particles. Let us outline the steps in derivation of carrier concentration as a function of space and time, and current density as a function of space and time. Let us assume that we have n electrons in the device. So this is the complete device. Okay? So in this whole device you have capital N electrons. Okay, and we are looking at the states of each of these electrons. That is what we are doing here in this approach. If you regard the carriers as waves, what you will do is the following. First, you will solve the probability amplitude function psi x t for each carrier I, where I varies from 1 to n, and this is done using Schrodinger's equation. Now when you are doing this solution, you will ignore the crystal potential and replace the mass of the electron in vacuum m naught by mn, so that the solution becomes easy. Once you have obtained the probability amplitude function or the wave function for each carrier, then you will use this formula modulus of psi I square for each carrier and sum it up for all the n electrons, and the result will be the carrier concentration n. The carrier density Jn on the other hand will be obtained by summing up this quantity shown here by this equation. Now let me clarify that at this point we are not discussing how these equations are derived, right? We are simply outlining what is the procedure. We will discuss meanings of this equation in detail a little later. So looking at this equation for Jn, here let us explain the term. This is h cross divided by 2 times the effective mass, and you have a j coming in here because the amplitude wave function is complex. Now psi I bar is the complex conjugate of psi I. So you are using a gradient here to find out the current. So very simply stated, the current is nothing but current of electrons is nothing but the probability current, because the probability is varying with distance. There is a gradient of the probability, therefore you are getting a current. Now you know that from your knowledge of Schrodinger's equation, the modulus of psi I square is nothing but the probability distribution function. More details about these equations we will discuss later. Let us look at the next viewpoint, individual carrier viewpoint, wherein you regard the carriers as particles. Now in this, the first step would be to solve the state of the particle or electrons, each of the electrons, using the Newton's second law. So solve for the position xit and momentum pit, which is equal to effective mass mn into the velocity, and do it from Newton's second law. So while the state of a particle is described in terms of the amplitude wave function psi I, which is the function of x and t in the case of the wave approach, in the case of the particle approach, each electron state is described in terms of its position x and momentum p. So this is what you are solving from Newton's law. Now what you do is, after you have solved for the positions of all the n electrons and the momenta of all the electrons by Newton's second law at any instant of time, identify the delta n electrons having their location xi's in local volume delta v. So these are your n electrons, and now this is your, let us say, local volume. In that you find out what is the number. Okay, this local volume is chosen around the point at which you want to find out the carrier concentration and the current. So delta n electrons are the electrons in this local volume, and you are obtaining this number by counting how many electrons fall into this local volume. Okay. Now similarly, let us say the local volume is delta V. So if I divide this delta n electrons by delta V, I will get the carrier concentration at this point. So that is what we are saying here. Carrier concentration n is equal to delta n by delta V. Now you can get the current density also from this information. Now for this delta n electrons, find out what are their momenta, pi, and then sum up their momenta after dividing by the effective mass, so that you get the velocities essentially here, and then you divide by the local volume which incorporate those delta n electrons, and you get this current Jn. So here we are saying that find out the momentas of each of these delta n electrons. Okay. So if I expand this picture, say it may be something like this. So this is the local volume, in which you have these electrons, and each electron has some momentum. So you are solving for this momentum from Newton's law. Then you are summing up all these momenta. Okay, that is what you are doing to get the current density. Of course, you are dividing by the local volume, so that your current density comes out in the proper dimensions. Now let us look at the particle approach in some detail. The most fundamental approach is actually the wave approach. However, the wave approach is sophisticated, and it helps to discuss the particle approach first to understand the wave approach much more easily, much more comfortably. So that is why, though the most fundamental approach is the wave approach, we are discussing the particle approach, the individual carrier viewpoint with carrier as a particle first. Now in this approach, the state of the particle is solved using Newton's second law. So let us look at the Newton's second law. It says rate of change of momentum with respect to time is equal to the impressed force. When you write the Newton's second law in this form, it reflects conservation of linear momentum. So we have said that our transport equations will all be some form of conservation or balance equations or continuity equations. Then we also said that they will have the form of the familiar whole continuity equation, wherein you have a time derivative on the left hand side and a space derivative on the right hand side. Now where is the space derivative here? So you see, you may write the force as negative gradient of potential energy. Okay, and now when you do that, you have a space derivative on the right hand side. Now in practice, often we use this form of the Newton's second law, wherein the rate of change of momentum is written as m naught into d square x by dt square, where x is the position of the particle. This is nothing but force is equal to mass into acceleration. Here there is a tacit assumption that the mass is not changing with time, it is constant. That is why it has been removed outside the differentiation operation, and this is equal to force. Let us look at the Newton's second law for electrons in a semiconductor. In other words, we want to see what are the forces acting on an electron in a semiconductor. Now this is what is described here in this equation. So the force on an electron can be due to applied electric fields or built-in electric fields or the crystal forces, which includes the atoms, their nuclei, positively charged nuclei, and other electrons or holes. Okay, it can be other carriers here more generally. Then the force, there is additional force apart from these forces, namely the scattering force. So while the forces due to applied electric field, applied built-in field, built-in field and the crystal force electric fields are expressed in terms of the electric fields, the scattering force has been simply left in terms of the force itself. This is a random force. Okay. Now let us see some example of how these applied built-in and crystal potentials or crystal fields, how they look like. Now here is a typical variation with x of EA plus EB, and below that you have the crystal potential as a function of x. First let us look at this EA plus EB. How do you get a shape like this? Supposing you take a p-n junction and this is the depletion layer. Supposing you are looking at the picture under equilibrium, then you know that there is a field from right to left, n to p region. This is a built-in field, and if I plot that field, it will look something like this as a function of x. Over and above this, I may superimpose an applied field. For example, if I am applying a reverse bias, then I am superimposing an electric field in this direction because of the applied bias. So effect of this also will get added here, and so this electric field picture will move down. Okay, there will be, this area will increase something like this, and then you will have fields going here. Okay, so that is how you are getting a shape like this for the applied and built-in electric fields here. Now let us look at the shape of the electric field due to the crystal atoms and other electrons or holes. How do you get a shape like this? First let us look at the field between any two nuclei because of the nuclei alone. So you have a positively charged nucleus at this point and another positive charged nucleus at this point. Okay, let us see what is the field picture. Supposing I have a positive charge here and I have another positive charge here. Now I want to plot the electric field between these two charges. Supposing I take a test charge and it is somewhere here, it will experience a repelling force from this point, which is in this direction, and it will experience a repelling force because of this charge, but the repelling force because of this charge will be smaller than this because this charge is closer to this charge. So therefore the other force can be shown with a shorter arrow. So the net force therefore is in this direction, positive direction. So therefore at this point, if I plot the electric field, it will be some positive value. Okay, this is x and I am plotting the EC, crystal electric field. If I move closer to this point, then the field will be more. So that is how you are getting some sort of a shape like this. Now if I move this side, then my net force will change direction. It will be in this way because the force because of this charge will dominate over the force because of this charge. So therefore your field will be negative at this point in this direction, and that is why you get shape like this. Okay, so this is the shape. Now you can repeat this for every pair of atoms, and you can then adjust this picture by taking into account the effects of other electrons and holes. So you see there are millions of electrons and holes, and you are looking at the force on a single electron. This is the so called single electron approximation. That is how you analyze the carrier transport in a device. So effect of all the other carriers can be absorbed by adjusting this field picture a little bit. Okay, so the net effect is what is shown here. So that is how this field picture is arrived at. The distance between two atoms is equal to a, and here this is the one end of the crystal, and here you have the other end. Now this picture is fairly complicated. Let us say we are working with this equation. What approximation or simplification can we make? Now you know that we make the significant approximation, namely the effective mass approximation, to simplify the effect of fields on the electron. So in this approximation we ignore the crystal potential, rapidly varying crystal potential. So it turns out that the applied and built-in potentials vary much more slowly than the crystal potentials. Okay. So the effects of the crystal potential, therefore we are ignoring while solving, but absorbing their effect in the effective mass. So when we cross out this ECX term, we change the m0 to mn to accommodate the effect of this. This becomes a significant simplification because now we are left with only this slowly varying potential. Okay, its effect can be analyzed easily, and of course the scattering potential. So now our equation has changed, m0 has been replaced by mn. Let us discuss how we solve an equation like this. So the first integration of this equation gives you the velocity at any instant of time and the momentum, which is nothing but the effective mass into the velocity, and the second integration yields you the position x of t. The initial conditions required for solution are the initial velocity or momentum and the initial position. So p0 and x0. Let us apply this procedure to a couple of situations. The first situation we have is an electron between two collisions in a uniform semiconductor under equilibrium, that is a free electron with an effective mass mn. So we are considering a situation where an electron is not acted upon by any forces. Okay, crystal forces we are ignoring, we are taking their effect into account in effective mass. Okay, so we are only concerned with applied or built-in forces. Further, since we are talking in terms of the picture between two collisions, the scattering forces are also not considered here. Now what will the solution look like for this case? So f is equal to 0. So here right hand side you set equal to 0. Then initial conditions are p0 is equal to effective mass into the thermal velocity. We are considering a semiconductor under equilibrium. So this thermal velocity is given by square root 3 times the Boltzmann constant into the lattice temperature divided by effective mass. Of course this quantity is under the square root sign. Now let us assume that the initial position of the particle is 0. This is an arbitrary reference that we are assuming. Now let me just clarify one thing. Why is it important that the semiconductor be uniform? Now we said there should be no applied forces, rather there should be no force on the electron. Now we have said that the force on the electron can be due to built-in fields or applied fields. So the non-uniform semiconductor will have a built-in field because of non-uniform doping. So we are eliminating any such built-in fields by suggesting that the semiconductor be considered to be uniform in doping. Now what is the solution? The solution looks like this. So the momentum as a function of time is obtained as p0 itself. So the first integration of this equation with force equal to 0 gives you the fact that momentum remains constant and equal to the initial value. Now the second integration gives you the position x of t, and this varies linearly with time, it increases. So x of 0 plus p of 0 by mn, which is nothing but the thermal velocity into time. That is how the position of the electron will change. Let us look at a more complicated situation, namely an electron between two collisions in a uniform semiconductor, but now subjected to a spatially uniform steady state electric field E. So there is no built-in field in the semiconductor, we are only having an applied field. Again we are not considering the scattering forces because we are considering an electron between two collisions. Now what would the picture look like? Now here f is constant equal to minus q times E. Let us draw a diagram for this. So this is the picture. So this is the electric field that is applied, E, and there is exerting a force on the electron. Now under equilibrium, the earlier picture, so the electron was moving like this. Okay. So here you can see the position of the electron is changing linearly, that is with time. Okay. So as when I follow an electron between two collisions, say between this point and this point, its position changes linearly. Here equilibrium and E is equal to 0. So both EA is 0 and EB is 0 because semiconductor is uniform. Here EA is non-zero, but EB is 0 because this is uniform semiconductor. So effect of EA is what we are trying to analyze. Now your initial momentum will be Mn into V thermal, where please note this carefully, the thermal velocity can be different from the thermal velocity under equilibrium. It is given by square root 3 times Boltzmann constant times the carrier temperature by Mn. It is not the lattice temperature. Under equilibrium the carrier temperature is same as lattice temperature, but when you are applying a field, the field could be high though it is steady state, and therefore the random velocity of carriers can increase over the equilibrium value. Okay. So that is what has been taken into account here. The carrier temperature can be higher than lattice temperature. Now as in the previous case, let us assume that the initial position x0 is 0, the reference is 0. Now what is the solution? When you integrate this equation the first time, when you integrate this equation the first time, you will get the momentum varies linearly with time. Okay. The force is contributing to the increase in momentum. Its position of the particle on the other hand varies quadratically. So this is equal to x of 0 plus thermal velocity into t, there is nothing but p0 by mn into t, plus half of acceleration, force by effective mass, into t square. This is a familiar equation that we have come across in our school days. Now what is the trajectory it look like? So now if you see, these portions which were shown as straight lines would now look curved. So when the electron is moving, it would look like this, right? So this curved nature is coming because of the square law dependence on the temperature, on the time, I am sorry, on the time. Now similar approaches can be used in determining the state of the particle, including the effect of scattering forces. Okay. Supposing we have determined the position and the momentum of particles at different instants of time. So we have n electrons in the device, these are the n electrons, and for all these n electrons we have determined their positions xi for different times and the momentum pi at different times. We have this information, suppose, using the procedure that we have just discussed. Now how will you determine the current and the carrier concentration? So let us look at that. Estimation of the carrier concentration as a function of space and time and current density as a function of space and time from the particle viewpoint. So at any t, the location excites of the n electrons within the device determined from Newton's second law yields the number delta n of electrons in the local volume delta V located at x, leading to this information about the carrier concentration at that x and at that instant of time delta n by delta V. So again this is the picture, this is the local volume from a knowledge of xit and pit for all the n electrons. I find out the electrons which are present in this local volume, then I take the ratio of this number to this local volume, I get small n, and similarly I find out the momentas of this delta n electrons, and then from this moment information I get the current. So that is the next step. From knowledge of PITs of the delta in electrons in delta V, we derive Jn of x comma t equal to minus q by delta V into sigma pi by mn, where the summation is done over the delta n electrons. Let us now move to an assignment for you. Explain how Newton's second law dPi by dt equal to f of x comma t and Gauss law for electric and magnetic fields, that is divergence of d equal to rho and divergence of b equal to 0, represent continuity or conservation equations. So please show how these equations can be cast in the form of the whole continuity equation, for example. That is the assignment. Next, let us discuss the individual carrier viewpoint in which the carrier is treated as a wave and see how we can determine the carrier concentration and current density. So here we use the Schrodinger equation. The Schrodinger equation is written out here on the slide. Let us just read it out once. J, which is the imaginary quantity square root of minus 1 multiplied by h cross multiplied by time derivative of the wave function psi, which is the function of space and time, is equal to minus of h cross square by 2 m naught into del square of psi plus the potential energy function u, which can vary with x and t in general, and psi multiplied by psi of x comma t, so wave function psi. Now the first step would be to familiarize ourselves with this equation and see it as of the same form as the whole continuity equation. So let me write the whole continuity equation. Dou p by dou t equal to minus 1 by minus dou jp by q, that is the flux of p, by dou x plus some generation and recombination rates. Okay. Let us write down the equation for the Schrodinger and show that it is coming out in the same form. So the quantity we are dealing with in Schrodinger's equation is psi, which is the wave function. So we replace p by psi. So we have a time derivative on this side. Then the flux of p, that is what is coming here. So the flux of psi. Now you recall in the previous lecture we had said the flux of a quantity can be put in two forms. One is the product of the quantity into the velocity, or other form is the flux is proportional to gradient of the quantity. Now it turns out in the context of the wave function psi, the flux due to the probability, it depends on the probability gradient. So the flux really depends, the flux of probability is proportional to the gradient of psi. So the quantity here we should put in terms of the gradient of psi. Now if you take the divergence of this gradient of psi, then you will end up with a del square term, right. Now further, flux is proportional to minus gradient of psi, because the current is from higher probability to lower probability, just as the current is from higher hole concentration to lower hole concentration if you assume diffusion. So when I take this negative gradient of psi and take its divergence and put the negative sign, this will get converted to del square. So plus del square psi is what is coming here. Let us right now not bother ourselves with the constant that comes here, we will put that later. Now plus or minus whatever a source term. Now following this approach where you find that, for example, the sink term here consists of the quantity P, which is coming here, for which we are writing the equation, multiplied by a constant, that is 1 by tau P. So here similarly there will be a term proportional to psi, and it turns out the proportionality here is the potential energy U. So this generates probability, therefore there is a positive term, this is a positive sign here. This quantity together represents some sort of generation or recombination, source or sink. So here we have a source proportional to psi, therefore there is a source, therefore it is a plus sign here. Now let us complete the picture by putting the coefficients. Now U is potential energy. Now you recall that the Schrodinger equation, the right hand side terms can be regarded as kinetic energy and potential energy. So kinetic energy is written as, in the classical terms, square of the momentum by mass, and momentum is of the form h cross k in the wave format. So I can put here h cross square, and when I take del square of psi, since psi depends on wave vector k multiplied by the x dimension, I will get the k square term out of this. So this quantity becomes h square k square. So now divided by the mass, so 2 times m naught, that is what is coming here. Now when you come here on the left hand side, to make it dimensionally appropriate, we must put one h cross over there. Now still it is not complete, because we recognize that unlike P here, the psi is a complex quantity. Okay? Therefore when you differentiate, the psi will be having a function of the form e power j omega t, for example. We will discuss this point in detail later. Right now just accept some facts. So when I take a time derivative of this quantity, I will get a j out. So one derivative I get one j out, therefore you get a j here. Similarly, the psi also depends on the x in a similar form, that is also a complex, the function e power j k x. So when I differentiate this with respect to differentiate this with respect to x, one differentiation will give me one j term, and another differentiation will give me another j term. So product of j into j square is -1, therefore you get a negative sign here, because there are two derivatives, double derivative here with respect to x. So that is what is the Schrodinger's equation. So you can easily see that it is of this form of the whole continuity equation, right? And therefore now hereafter you should not have any difficulty in remembering the various terms and how the various constants arise in that term, in that equation. Quickly, some 2 points about this equation. The action on the particle is specified by potential energy U in quantum mechanics, but force F, which is negative gradient of potential in classical mechanics. So you see, in Newton's law we used the forces to solve for the state of the particle, whereas here in quantum mechanics, in the Schrodinger's equation, you have the term U which represents the action, and this is nothing but the relation between this potential energy and force is what is given here. Now that is a very interesting and important point, that in quantum mechanics we always talk in terms of the potential energy, that tells the action on a system, whereas in classical mechanics we always talk in terms of the force. Just one more point, this equation and Pauli's exclusion principle together explain most of the solid state phenomena. So like, if you want to explain the phenomena related to electromagnetic fields, you have the 5 equations, the 4 Maxwell's equation and the Lorentz force equation, everything can be derived from there. Similarly, if you want to explain phenomena based on quantum mechanics, there are 2 things that you need to consider, the Schrodinger's equation and the Pauli's exclusion principle. Based on this, everything can be explained. Now you might wonder, so what happened to the de Broglie's relation and what happened to the Planck's relation? So de Broglie's relation is momentum is equal to h by lambda. Lambda is the wavelength of the wave, and Planck's relation is energy E equal to h times nu, frequency of the wave. Now we will show that the Planck's relation emerges from the time dependent part of the equation when u is a function of x only. So here, if u is a function of x only, does not depend on time, then Planck's relation can be shown to emerge while solving the equation. Similarly, de Broglie's relation emerges from the space dependent part of the equation, that is this part here. This is time dependent, here you have time derivative, and this is space dependent part of the equation when u is a constant. So you should set this u as constant, that is the particle is free from forces. So de Broglie's relation applies only for a free particle. Okay. Now this we will establish when we discuss the solution of the Schrodinger's equation, in the same way as we had discussed the solution of Newton's laws. Now we have come to the end of the lecture, so let us quickly summarize the important points. In this lecture we continued our discussion of the transport equations. We explained the 4 levels of descriptions of carrier transport from microscopic level to macroscopic level. The most fundamental level was individual carrier viewpoint regarding the carrier as a wave. The next level was individual carrier viewpoint regarding the carrier as a particle. Then the next level towards the macroscopic level viewpoint was taking the carriers in groups and looking at them in terms of their distribution over momentum. And the most gross level macroscopic viewpoint was looking at carriers within a local volume in terms of their average concentration, average momentum, and average energy. And we said that this macroscopic description in terms of carrier concentration, average momentum, and average energy is the one that is generally applied in most cases. Then we outlined the procedure of deriving the device current and carrier concentration in the individual carrier viewpoint, assuming the carrier to be a particle. And we said we will do a similar exercise for the individual carrier viewpoint regarding the carrier as a wave, and we just began this discussion and introduced the Schrodinger's equation, which is a fundamental equation in this particular approach. We showed that the Schrodinger's equation can be regarded as a conservation or balance equation which talks about the balance of probability, and it can be shown therefore to be of the same form as the whole continuity equation. Now in the next lecture we will discuss the Schrodinger's equation for electrons in a semiconductor and also the solution of this equation and how to derive the current and carrier concentration.